when we calculate that we apply the formula where we are stress critical is equal to pi squared E over L over R squared, right? So now we want to determine our L over R. So this will be equal to square root of pi squared multiplied by 200 times 10 to the power 9. And then we divide this by L by pi squared by 250 times 10 to the power 6. And over here now we get 88.86, right? So you all still remember that we sketch, right? We sketch a graph. So this graph that we sketch, we have our x-axis. So our x-axis is running on the ratio L over R. We're going to start with 0, 50, 100. Oh, no, let me go. What scale did I use the last time? I can't remember. Oh, 20s. Okay. 20, 40, 60, 80, 100, 120, 140. I'm going to check, do I need more than 140? I do need more than 140. There's one that later on we'll do 160 and 180. Okay, so I'm going to sketch this out. And then on the y-axis, right, you have 100, 200, 300, and this is stress, and this is megapascal. And we calculate our L over R is equal to 88.86. Okay, so we're going to sketch a line. One. We're going to sketch a line. And this line over here, at this point, okay, and this line is 88.86. At this point, okay. So what it means, if it's less than 88.86, right, we all remember, we use over this side, right, structure will not buckle. And then on the right hand side, the structure or must analyze buckling. Because when we have a structure that will buckle, what happened is the stress level that it can withstand the load will what? Will drop. Okay. The bigger your L over R ratio, the lower the critical stress the structure can take. Right? You all remember this graph, right? We did this last week. Okay. So now this, for this case, is for both ends T. Okay. Then we're going to look at another situation. Okay, we're going to look at another situation. So the next situation that we are going to look at is we're going to have the ends. Okay, so if you look at this diagram down here now, now we have what? We have both ends are what? Or one fixed end. So condition, did I put condition number 1 or I just put condition? Yeah, condition number 2. Is where you have one end fixed. And then you have the other end. You have the other end. And then one end fixed, sorry, one end fixed and one end free. Okay, so let me teach you how to identify what is fixed and what is free. Okay, so if we were to sketch the centroid, yeah, I'm going to sketch the centroid before deformation. Okay, so this is the centroid before deformation. Okay, so this is our centroid. So when is it? So let's start from point A. So point A is what we call free. Okay, point A is free. And when we classify it as free is when the load P shifted away, or point P, load P is allowed to shift away from the centroid, right? You can see at our centroid, point P has shifted away a certain distance. If we go back to pin, right? You go back to pin, right? The structure is already buckling already, right? But the load P is still aligned to the what? Aligned to our centroid. And this is because of the restriction in motion in the X direction, okay? You can see that, right? Whereas when it's free, right, it's allowed to shift. So now if we were to look at the condition at point A, right, we know that X direction at point A is not equal to 0. Y direction at point A is not equal to 0. And moment at point A is also not equal to 0, right? Why is that? Because again, how to recognize it as a moment? If you draw at point A, you were to draw a vertical line coming down, right? You draw a vertical line coming down. And then at point A, you draw a tangent. Okay, so this is the tangent to point A. What do you get? You get a slope. So over here, theta is not equal to 0. Sorry, moment is equal to 0. I do apologize. Okay, moment is equal to 0. Right? Now at point B, right, point B, what we see now at point B, right? So point B is what we call fixed. Okay, point A is free, point B is fixed now. And why is that? Okay, it's because X is equal to 0, no motion in the X. Okay, let me put this as X, Y, this is rotation, Y, Z. Okay, and then Y is also equal to 0. So you don't like movement in X and Y, no motion at all. However, okay, moment is now not equal to 0 because theta is equal to 0. Okay. So if I were to over here, this is where point B is, right? If I draw a line, the line is in fact parallel to the what? Parallel to the centroid. Okay, it's a straight line, right? So when this case, when moment is not equal to 0, theta is equal to 0, this is what we call this as our fixed point. Okay, so whether is it free, pin, or fixed, you have to watch the moment. So let me do this quickly. So when free, when m is equal to 0, okay, it's either free or pin. Okay, so you know when it's free is where the what? Free of pin. You're right, Eugene. Or pin. It's free when the P is allowed to shift what? It's free when the P is allowed to shift away from the centroid. Pin, no shifting, right? So when M is not equal to 0 means its value is usually what? Fixed. Okay. Whether is it fixed or whether M is equal to 0 or not, if you can't visualize it, look at the what? Slope. Okay, it will tell you. Now, so how does this affect now? So when that's the case, right? That's the case, LE, when one end, one fixed end, and one free end, right? LE is equal to 2L now. Okay, LE is equal to 2L. So it's not equal to L, right? So now if we were to use Euler's formula, we calculate critical stress, right? So now this is equal to pi squared E over LE over R squared, right? So now we know that LE is equal to 2R. So this is equal to pi squared E. So now this is equal to 2L over R squared, okay? So you ask me, okay, right, we have LE is equal to R squared. So what? Okay. So now if we were to calculate our 2L over R, right? So we look at 2L over R, we have square root of pi squared E over by stress critical, right? So the L over R, so if we write this in terms of L over R, this will be equal to 1 over 2 multiplied by pi squared E over stress critical. And if we use the same value as before, so this is half multiplied by pi squared multiplied by 200 times 10 to the power 9. And then we divide by, what was it? We divide by 250. Okay. So what will happen now is this. Okay. So shift pi times by 200 divided by 250 power 6. Square the whole thing divided by 2. So it now drops down to 44.43. So what does this 44.43 mean? Okay, so let me get the same graph like what we have drawn earlier. And let me paste this here. So what does this mean now? Okay, so this means the structure, right? The structure will buckle or will be more sensitive to buckling. Okay, so now we drop this to 44.43. Okay, now we drop this to